So my name is Eliana. I'm a researcher at Imperial College London, and I'm going to talk about some recent work on localization and particle filters with a view towards an application in geophysical data assimilation. And this is joint work with my postdoc supervisor, Dan Crisan. So first of all, a little bit of advertisement of our research group. So I'm part of a project called STUAD. STUAD stands for Stochastic Transport in Upper Ocean Dynamics. And it's funded by a ERC Synergy grant between 3 institutions. So we have Imperial in the UK, and then Ifremer and RIA in France, and we have 4 PIs. And of course, within the group, people do different things from data acquisition, data analysis, numerics for SPDEs, modeling, calibration. I work, as you can imagine, on data assimilation. And with regards to data assimilation, our goal is to create or to come up with particle filtering algorithms that are stable, so they don't degenerate despite the fact that we are dealing with very high dimensional problems, and they are also fast, so that in fact they can be viable for practical applications. So I am not going to talk almost anything about the models that we use apart from this slide. So we work with SPDs, so stochastic partial differential equations, in 2 frameworks. One is called LU, location uncertainty. It's developed by Etienne Memen at INRIA, and the other one is called SALT, stochastic advection binary transport, developed by Daryl Holm at Imperial. And nice things about these models is that they introduced stochasticity within the geophysical fluid dynamics equations in a physical way. So features like conservation of energy, conservation of helicity, or Kelvin circulation theorem are preserved, despite the fact that we're working with a stochastic system and not just the deterministic one. So in particular, the model I will be using, which is the one I will test my particle filters on, is a stochastic rotating shallow water equation. It's from the SALT framework. So these are the equation. If you just ignore for a second the stochastic term, so this bit of the second line and this bit of the third line, you just recover the deterministic rotating shallow water equations, in which, okay, u is the velocity field, eta is the height of the waves. We work in a non-dimensionalized setting, so all the scales are encoded into the Rossby and the Frude number, so non-dimensional numbers. I will work only on a square, 1 by 1 square. I put viscous in bracket because I have a little bit of viscosity, just enough to ensure stability of the numerical scheme. So in fact, it's so small that we are closer to the envisioned setting. And now regarding the stochastic term, a way to understand it, or at least my way to understand this stochastic term, is to look at this transfer term here in the dynamics of the velocity field and think about perturbing, so u dot grad u, and think about perturbing u by adding a spatial Gaussian noise, both here and here. And then this is the term that comes out. And of course, then eta is coupled to the velocity, and therefore you have a stochastic term coming out for the dynamics of eta as well. In terms of the circle here, I don't know if everybody's familiar with it. This is just denoting a Strotonovich integral. If you're not familiar, then think about it as an Ito integral with some drift correction. So this is the model I will use. As you can see, is very highly nonlinear. Right, so these are 2 realizations of the stochastic partial differential equation that I showed you above with different parameters. So this is Frude 0.3 and Rossby 0.9, and this is Frude and Rossby, both very small, 0.05. And you can see very different behaviors of the SPDE. I call this the sub-mesoscale setting, and this is the mesoscale setting. Clearly, I will attempt, I will show you results for data assimilation in both cases. Clearly, the left one is going to be harder to capture. We can see already just from the video. Okay, so I don't think I need to spend a lot of time on this slide. It's just to remark the fact that stochastic filtering and data assimilation are in fact 2 sides of the same coin. So I come from a stochastic filtering background. So for me, the easiest way to understand the data assimilation problem is to think about a filtering problem in which model dynamics, distribution of the noise, sensor function are all unknown. So in a way, a data assimilation problem is just a harder filtering problem. Very often in data assimilation, we talk about twin experiments in which we create synthetic data by running, in this case, it's going to be my SPD, my rotating shallow water SPD. So I just get a realization of it, and then I perturb it and get some observations out of it. And the model that I use to run my signal is the same model that I would use to run my ensemble members. This is basically translating the data assimilation problem back into a filtering problem. So all the results I will show you today, all the numerical results, are for a twin experiment. So in fact, I am just solving a stochastic filtering problem. Right. This dichotomy between filtering and data assimilation is, in the end, the main reason why we decide to work with particle filters. Particle filters are known to converge to the actual filtering distribution as the number of ensemble member goes to infinity, and this holds in full nonlinearity. This does not mean that other data assimilation methods do not work. This just means that we like to have some kind of theoretical backing for what we do. Now, one of the reasons why particle filters are not widely employed in practice is the so-called curse of dimensionality. Now, there are early results about this that basically just tell you that as soon as you have dimensions or too high dimensional problems, the particle filter is going to collapse. But it should be noted that these results regard a very basic particle filter or the bootstrap particle filter. Now, of course, a bit like for ensemble Kalman, people do inflation, localization, and so on to get better results. We can do the same for particle filters. So we can modify a particle filter from the bootstrap, and we can get particle filters that are stable in high dimension or can be stable in high dimension. If somebody is interested in a theoretical result in this direction, I suggest this paper from 2014 published in Annals of Applied Probabilities. Okay, so what is an example of a particle filter that can be stable in high dimension? Well, it's a particle filter that has a bootstrap. So basically, we resample after we compute the weights from the likelihood. And then we add jittering and tempering. Jittering is a procedure that comes from the MCMC literature. And the idea is to increase the spread of the ensemble after resampling. So we go and target the ensemble spread. And then tempering instead targets the degeneracy of the weights. I can tell you more about these two algorithms later if you have questions, but these are not new. So I would rather talk about localization, which is the actual contribution of our work today. Okay, so in any practical geoscience data assimilation problem, observations are going to be localized. So I'm going to have that my observations are at some specific points in the domain. So the intuitive justification for localization is the fact that if I have an observation down here, and based on that observation, I update my ensemble members, well, then that observation should have relatively little impact on the update of the ensemble members that happen on the top right corner instead. So this is intuitively. In practice, what I'm trying to do is I'm trying to break down a very big problem, data assimilation problem, into lots of smaller problems. This helps with weight collapse. So it helps with the stability of the algorithm itself. And then if I come up with an algorithm that is scalable, so if I come up with, if in my procedure of breaking down the problem into smaller problems, these smaller problems can be solved in parallel, then my problem is scalable. And if I have a large amount of GPU or CPU available, I can save a lot of computational time. On the left here, you can see a domain, a square domain, and you can see some grid points equispaced in the domain. So my domain is 128 by 128 grid points, and I'm observing only eta, the height of the waves. So I'm never observing the velocity field. And this is a type of observations that I will take, so just unequispaced grids of points within the domain. And then this is another type of observation that I will take. So these are just a vertical line that then I will move cyclically throughout the domain. Okay. Main issue with localization are when it comes to particle filter are discontinuities in the state space. So let me expand a little bit on our algorithm and why there are these issues. So this is my domain. It's a square, and I am gonna break it down. I'm gonna decompose it into, in this case, it's 9 smaller subregions. And the idea is that within each subregion, I have some observations, and the observations that are contained in a region are going to have a lot of weight or full weight when working on the particle filter on that subregion, and are going to have much less weight when I'm dealing with the particle filters outside that subregion. Now, the first thing to notice is that my decomposition is not a partition. So I have overlap between my subregions. So that means that here at the interface between these two regions, I will have 2 copies of the same particle. And here at these corners, I will even have 4 copies of the particles. And this is going to help with interpolation. Now, the other thing that is going to help me is the fact that I'm going to define a local likelihood that is not completely going to ignore the observations that are outside my region, but it's going to just weight them. So I'm going to use a type of Gasperi-Kohn localization function. This is going to be different for each subregion. In fact, you can see there is J. J is the index that of the subregion, and it's going to give full weight to observations that are within the subregion, and then some value between 0, 1, of course, closer to 0 the further away you are from the subregion, to observations that are outside. And using this Gasperi-Kohn localization function, we define a local likelihood. So this is, again, it's going to be a different function for each subregion. It's basically defined, so if we assume in this case normal observation noise, so it's basically defined as you would expect the local log likelihood, with the difference that each observation is weighted by the Gasperi-Kohn function, and that when we compute y minus h of v, where v is whatever numerical field I have defined on my domain, I take the restriction of v onto the subregion. And then there are other parameters coming up here, but this is the main idea. Right, this one, I don't really need to tell you anything much about this. This is just, okay, at the end of each assimilation step, I end up with a bunch of local ensembles. So in the example from before, I had 9 subregions. That means I have 9 local ensembles. All these ensembles have done resampling, jittering, and tempering independently, in parallel one with the other. I need to somehow reconstruct a global ensemble, and you just do it in the most sensible way that you can think of, using all the fact that you have these overlaps that allow you to just create an easy interpolation. Okay, these are the error metrics that I will use to assess the efficacy of my localization procedure. So the first 3, so you can see I'm computing them for both the velocities and also for the height, despite the fact that the velocities I'm not really observing. The first 3 are computed on the whole domain, independently of how many observations or how many locations I'm actually observing. While the other 2, they are computed only at the observation points, and they are summed and then averaged over the number of observation points at each assimilation time. Okay, so the first thing we want to check is that our localization procedure is not adding a lot of error to our particle filter. Now, this is a toy example. This is an example that, despite being high dimensional, my particle filter works. So this is the particle filter with jittering and tempering, not just bootstrap, of course. And what I'm showing you is 2 experiments. So I have an observation grid of 4x4 equispaced within my domain, and then 32x32. So clearly I'm observing much more in the case of the orange lines. And I'm running a local particle filter. You see the solid line, and a particle filter with the dotted line. And we see that the errors are basically the same magnitude, which means that my localization is not adding undue error despite the interpolation procedure. Now, the other thing that we can notice here is that clearly observing only a 4x4 grid within a domain that is 128 by 128 is not enough. So This is also, you can see it up here as well. So here we have the RMSE and the CRPS of eta. So this is the height. And we see that in the 4x4 case, these are extremely oscillatory, while in the 32x32 case, we have stability more or less around 0.15. And now this makes you wonder, okay, how many points do I need to observe before I somehow reach optimality? So here I just add more and more and more grid points up to the point in which I'm observing all of the domain, perturbed, of course. And we can see that after 16 by 16, the error does not improve that much. So that means that despite the fact that this problem is very high dimensional, it's also highly correlated in space. So as long as I'm observing enough of the domain then my error is as good as it gets, really. The other thing to notice is that I'm not observing U, but the error also for U stays somewhat bounded. Okay, for a particle filter, we know that if I increase or decrease the frequency of my observation, the error should increase. I'm checking that the same holds for the local particle filter, and we see it exactly the same. I'm in the green line, I'm observing every 5 time steps, then 10, 20, 25, 50, and 100, and we see that the errors increase accordingly. This is how you can visualize, for example, your particle filter. So here I have fixed allocation in space. In red, I am plotting the signal, its evolution in time for the first 600 time steps. And then in green, you have the ensemble members. And in light green, you have the posterior mean. And here I'm changing the frequency. So these are the plots that are related to the errors up here. And of course, the more I observe, the closer my filter is to the signal itself. Now, regarding the parameters of the local particle filter, one could think, okay, but I might as well localize as much as possible. So in this case, I have only 128 by 128 grid, but I am localizing 4, 9, 16, 25, and 36 regions to see what happens. And we can see that in effect, if we add more regions, eta, or the error for eta, does decrease, which makes sense because in each of my small local particle filters, I can match the signal much more closely. But at the same time, in the case of U, for example, that I'm not observing at all, and that is has the problem of interpolation error coming in, that because of the nonlinearity gets spread spatially, we see that it's the opposite. The more regions I add to my domain decomposition, the bigger the error is. So balance is necessary. And now the last experiment I want to show you is assimilation of a line. So this, again, we see a line that gets observed at different times. You can see the ensemble, you can see the signal. This is the height of the waves, and this is the velocities. This is in the mesoscale regime. So this, in here, it works pretty well. In the sub-mesoscale regime, as I told you before, this is harder. And of course, this is a much harder problem compared to the results I showed you earlier, because the results I showed you earlier were related to a grid that was equispaced around the domain. So I had information more or less everywhere, while in this case, I really have only localized information. And that means that when I am far away from that information, I don't have much to update my ensemble members. Few things that we are still working on. Well, the first one is to move on to an imperfect model. So I've worked on filtering, I've worked on a twin experiment. Now it's time to move on to a data assimilation problem. So use an imperfect model, creating first synthetic data, and then potentially even using real data. And then I'm also working on a few theoretical results to partially justify the localization algorithm. And the main takeaway is that particle filter, in particular local particle filter, can work in high dimensions. Thanks for listening.
Thank you very much, Eliana. That was a really interesting talk. I have, before I go to the geopad, I have one question about the localized, the interpolation that you were mentioning. So if I understand well, you have different particle filters acting for each one of the regions separately, and then at each filtering time, you create a global particle filter, or did I miss it?
Yes. So you have your ensemble. So you evolve it forward. You evolve it forward on the whole domain. So your prior is given by global particles. At this point, you can just restrict the global particles to the subregions. So you have a bunch of local particles or local ensembles. And in each of these subregions, you do your local particle filter. So you do your jittering, tempering, resampling according to the local weights that are given by the local log likelihood. So at the end of the assimilation step, you end up with, like in this case, 9 sub-ensembles, in a way, sub-particle filters that you have to merge together. And that's why you need interpolation. So you want to recreate your global ensemble, basically.
Okay, thank you. So now I go to the questions in the GeoPad. The first question is from Peter Jan van Leeuwen. He says, localized particle filters with some sort of interpolation have been around for a long time. The main issue is the stitching of the particles. For example, interpolation will destroy fronts, etc. What do you suggest to improve on just interpolation?
Yeah, that is a good question that has come up often. So all I can say is that the issue does not really arise that much, at least in the examples that I have tried to run. In the sense that if I compare a particle that has been interpolated versus a particle that has just run globally, there is no real difference between the two that you can see. Of course, the fact that the model is nonlinear and the fact that this is supposed to be a physical model means that I am destroying some of the physicality. I don't really have a good answer to this. I am also not completely sure how, if this is ever going to be solvable. I mean, every time you resample, you kind of destroy your particle anyway. So yeah, I am not sure. I'm not sure.
And we have time for one more question. There are several questions in the GeoPad, so I encourage all the speakers to take a look and answer by writing all the questions we don't have time to ask directly. But well, the second question is from Lars. He says, I suppose that the tempering will have a large influence in your experiments. How many steps do you use?
So this depends a lot. So the more observations you have, the higher is the number of tempering steps that you need. So and then of course this is also gonna be influenced by the definition of your jittering algorithm, because tempering goes together with jittering. So for example, one of the advantages of localizing is also that by solving the local particle filter, the particle filter locally in a smaller domain with smaller amount of observation, locally you have fewer tempering observations that you would have if you have to do it globally. But the answer to this is it depends on the parameters. It depends on the experiment itself. It can be around 5, it can be 10, it can be 100 tempering steps. It really depends.
Good. So there are 3 more questions that you can look at in the job and answer them there. So we're going to move on, and now I'm going to pass the sharing to Nachi